All right, let's get going on today's meeting. So today we are finally going to wrap up our look at the t-test, our introduction to inferential statistics. So just to kind of recap, we did the one sample t-test, we did the two sample t-test. Last time we began the paired t-test, and then today we are going to finish the paired t-test, go through a decision tree to make sure that you're always choosing the right t-test, and then finally take a look at why it's so important to choose the right t-test. So this is going to be our t-test wrap up, where we take everything that we've been working on, put it in a box, puts a shiny bow on it, so that we have it locked away and ready to use whenever we come across those situations. So once again, we're going to be relying on SPSS to do the heavy lifting. This is very important when we're doing the t-tests. It's going to become even more important when we get to ANOVAs, because the complexity of the calculations just keeps scaling. So SPSS is going to be your best friend moving forward. And again, the rest of this semester is all about inferential statistics, going from that sample and being able to objectively and intelligently and systematically say conclusions about the population. And then today we're going to continue with our Do It With Me demos, where you see live SPSS demos done in real time, so you can see some of the pitfalls that occur, but more importantly, the workflow to get to the correct analysis. All right, so that should say paired t-test and t-test wrap-up, but we'll continue on. So we're going to take a look at the paired t-test today, the Do It With Me demo. Same four-step process when we're doing any of these t-tests, because that is the four-step process for a hypothesis test or a significance test. And we're going to take a look at the Kahneman et al. Study that gave evidence that there are certain cases where your mind fools you and actually prefers situations where you experience more pain. And then we're going to take a look at the t-test decision guide, and then we're going to end it with 3 Do It With Me demos, again using that four-step process. But this time we're going to take a look at hypothetical data on the effects of a digital curfew on sleep quality in undergrad students. So a study that is designed to test if putting your phone away and putting all digital media away at a certain time before you go to bed, does that increase your sleep quality? And 3 different ways that that question could be investigated. And then we're going to see why, again, it's important to choose that correct t-test. So as I mentioned before, this is going to wrap up our look at t-tests by completing our look of the 3 types of t-tests. So we took a look at a 1 sample t-test. We took a look at the 2 sample t-test. And then last time we introduced the paired t-test. And again, just to drive this home, all of those are done following that 4-step procedure. So again, the more comfortable you get with this 4-step procedure, the easier it's going to be moving forward, because all significance tests follow this particular procedure. All right, so let's continue with the Do It With Me demo. Just a brief recap on that Kahneman et al. Study. So in this study, they wanted to investigate whether you could fool somebody's mind, you could fool somebody's recollections of their experience, so that they would choose to undergo a more painful experience rather than a less painful experience. And when asked if which situation had more discomfort, they would say that the shorter or less painful version had more discomfort than the longer, actually more painful version. So the way that they did this, they used a paired design where subjects would experience both of these conditions. So they had one group of subjects, one sample of, I believe, 32 subjects, and they experienced both of these conditions. So in condition A, treatment number 1, the subjects would place one of their hands in a ice water bucket, and that water was at 14 degrees Celsius, so it's incredibly cold, like ice bath cold, and they would have to keep their hand in there for 60 seconds. And that's painful. And then after a period, they would do their other treatment. And again, the order of these were counterbalanced to remove any order effects. So half of the subjects did the short trial first, half of the subjects did the long trial first. But importantly, the long trial duplicated the short trial. So in the long trial, you put your hand into that ice bath for 60 seconds and it was at the exact same temperature. And then for the final 30 seconds, the temperature was raised slightly to a still painful 15 degrees Celsius. So the question is, if you ask these subjects, hey, which of those two experiences that you went through did you find to be more uncomfortable? Which one caused you more discomfort? You would predict that logically they should say, well, treatment 2 produced more discomfort. Because at the very least, treatment 2 produces the exact amount of discomfort as treatment 1, plus whatever is going on during those 30 seconds. But Kahneman et al. Were studying whether or not you deceive yourself somehow, whether or not there are psychological processes that misinterpret your experiences. And maybe you would actually say that the short trial was more painful. You would actually rate that one as having more overall discomfort. So to see what happened, we're going to take a look at our hypothetical data here. So again, this data is based on the results of Kahneman et al. And we have these discomfort ratings over here, and these are on a scale of 1 to 14, 1 being the least discomfort, 14 being the most discomfort. And importantly for this analysis, the reason we're doing a paired test is because we have one sample of subjects and they're measured twice. So these two scores here, they belong to subject number 1. And they gave a discomfort rating of 6.6 for the long condition and 9.9 for the short condition. Here's another subject here, gave a rating of 6.8 for the long condition, 9.4 for the short condition. So every single one of these rows is a different subject. And you can see here in the calculations that have already been done, we have 32 subjects in the long condition, and we have 32 subjects in the short condition. And the reason those are the same is because they're exactly the same people. The same 32 that were in the long condition are the same 32 subjects that were in the short condition. And then last time, we set up the null hypotheses and the evidence for the alternative hypothesis and the alternative hypothesis itself. And again, it makes sense to our minds to write it this way. The mean discomfort in the long condition for the null hypothesis, the mean discomfort in the long condition is going to equal the mean discomfort in the short condition. But occasionally, and in your textbooks, you'll see it like this, saying that the mean difference between the two conditions is going to equal 0. And then the same thing with the alternative hypothesis, makes more sense to your mind and is accepted in statistical circles to say that the population mean for the long condition does not equal the population mean for the short condition. And again, remember, we're doing a two-tailed test because logically they should say that the short trial was less painful, but psychologically there's evidence or there's theories as to why they might say that the long trial was more painful. So we got theories going both ways. So we do a two-tailed. And then also that alternative hypothesis can be expressed as saying the population mean of the difference is not going to equal 0. Alpha level is 0.05, not explicitly stated in the paper, so we assume rightfully that is 0.05. And then the evidence for the alternative hypothesis is that if you take a look over here at the sample means, the sample mean for the short sample or the short duration, the short trial, is larger than the sample mean for the long trial. So the difference between those two will not equal 0. Or you can say that the mean sampled difference, the difference between the two sample means will not equal 0. All right. Now we go down to step 2. So in step 2, once again, we have to decide were these subjects chosen randomly, and then is the sample large enough? And one of the nice things about the paired t-test or the paired experimental design is that the answer to both of these is the same because they're both the same subjects. So was the sample for the long condition random? Yes, it was. They were randomly selected. Allow. Same for, try that again. Same for the short condition. And then was it a large sample or did it come from a normally distributed population? We don't know about the population if it's normally distributed, but it is larger than 30. So yes, we have a large sample for the long condition, and yes, we have a large sample for the short condition, because I'll say it one more time, they're the same people, it's the same sample. All right, so now we are going to open up SPSS. All right, so we are ready to go now with SPSS. So let's go to the t-test paired SPSS demo. And we need to take this data here and copy and paste it into SPSS. Now, one of the things that I like to do, I'm a lot more familiar with Excel than I am with SPSS. I know a lot of the shortcuts and techniques used in Excel better than in SPSS. So one of the things I like to do when I'm using SPSS is I will format the data in Excel so that it's in proper SPSS form, and then I'll just copy and paste it wholesale, and I don't have to worry about entering in, group names or anything like that. So we have an example of that right here, because in SPSS, if you recall, the big organizing rule for how to organize your data in SPSS is that every single row here is a single subject, and every subject gets their own row and no other rows. So we need to make sure that every single score of a single subject is in a single row. So these two scores belong to the same subject, they're in the same row. These two scores belong to the same subject, they're in the same row. That's the way our data is formatted in Excel. So we can just copy and paste both of those columns and then go over here to SPSS, paste those in, do that thing that it keeps making me do. And then we just Control V and paste that in. And that is formatted correctly. That is formatted correctly in SPSS. We are almost good to go. But what we don't have yet is we don't have the variable names in there. And this is when you want to go back to your data, check your labels. It goes long and then short, because you don't want to mislabel which one of these are. So we have long on the left, we got short on the right. So the var 0002, that's long, var 0003, that's short. So we go up here and we change that one to long, and we change that one to short. We go back, and now we have the data in a nice way. It's ready to go. It is properly formatted. All right, so at this point, we go to analyze. We go to compare means and proportions. And this one is extremely friendly. We're doing a paired t-test. SPSS calls it a paired samples t-test, exactly the same thing. So we click on that, and then we get to this dialog box here. And what SPSS is asking you to do is it's asking you which one of these two variables here is going to be variable number one, or pair number one here. Now we only have one pair, so we can do multiples if we had that design, but we only have the one pair. But what SPSS is asking is, well, which one is variable one and which one is variable two? So we're going to put in long as variable one, and then we're going to click on short, and we're going to just use the arrow to pop it in to variable two over here. Now, the order here, in terms of making your conclusion, it does not matter. The order here, whether you go long one or you put long in this as a second variable, the order doesn't matter. It just matters in terms of which direction you're trying to hypothesize in. And I'll show you what I mean in just a moment. But we're going to keep variable one as long, variable two as short. And this one is way better set up than the two sample t-test in SPSS, because let's say that we change our mind and we want to put long as variable number two and short as variable number one. We have these little arrows here, and you can just click on those and swap those all day long. But we're going to keep it long and short, long one, short number two. We're all set to go. Everything is good. We're going to keep the estimate of effect sizes. We hit OK, and we get this output here. Did everybody attain this output? Looks good? All right. Okay, so we're going to zoom in on this and kind of do our analysis, and I'll mention what it is in terms of that order and where it will pop up. So the first thing, always double check your sample statistics. So SPSS very nicely breaks it down in terms of, well, here's the long condition, and we have 32 people in the long condition, 32 individuals, and you double check your data and you go, yes, you're supposed to have 32. The mean is 9.85. You double check your data. Yes, you're supposed to have a mean of 9.85. Standard deviation, you can check that as well. This just gives you confidence going forward that you're doing things correctly. And it also prevents errors from occurring. And when you're dealing with statistics, as we're going to see in the last demonstration of the day, when you're doing statistics and when you're doing psychology, we're going from a sample to a population. We're going from a subset of people to making conclusions about everybody. And when you're making conclusions about everybody, you got to make sure and double check your data, make sure you're doing things correctly. So again, we can check the short data that we put in there, and we have 32 scores, n equals 32 scores, that's what it's supposed to have. 10.76, that is the mean that it's supposed to have. We can check the standard deviation as well. It gives us that information. Now we're very confident to go forward. Okay, the next thing, if there is one mistake that students typically do when they're doing the paired samples t-test, it's this mistake right here. They'll take a look at this table down here, and they'll say to themselves, I need a p-value. My question is asking me for a p-value, or I need a p-value in order to draw my conclusions. And hey, take a look at this. We got significance right there. One-sided p, two-sided p, that's wonderful. We have the p-values that we need. That table is a trap. That table you will learn about in grad school statistics. That is not an intro to statistics table, but SPSS puts it second. And I have seen many, many students go through their output, find that word that says significance, look at that thing that says one-sided p or two-sided p, and then just use those numbers. Do not use this table. This table is not what you're looking for. This table is what you're looking for. So resist the urge, resist that temptation to grab those numbers because they seem to be the ones that you're looking for. Pass that table on by, and we're going to go down to this table here that has the data that we're looking for. So this is the paired samples t-test table. It gives you the stats and the analysis for the paired differences. So what that means is it's going to give you the analysis for the scores on the long condition minus the scores on the short condition. And we have that right here. The scores on the long condition minus the scores on the short condition. SPSS will tell you which direction it went in. Now, we had ratings of discomfort. Ratings of discomfort, the higher they were, the more discomfort they had. The higher those scores were, the more pain that they had. And the prediction was that the pain in the long condition would be less than the pain in the short condition. And because we wanted that direction to be less than, right? Because our alternative hypothesis was that we were predicting the less than, that's why we have the mean here of minus 0.91. Okay, that was Kahneman's theory that he was trying to look evidence for. He did have the alternative hypothesis, which was why he did the two-tailed, but this is the one that made sense to his brain. This is the one that made sense to their minds. We're looking for less discomfort in the long condition, so we want a negative number there. Let's say that their thinking was flipped, and they were looking for more discomfort in the short condition. In that case, you would go back to your data editor and you would say, oh, okay, instead of going long minus short, I'm going to go short minus long, and it'll just make the mental gymnastics easier to do, especially if you start going into things where you're predicting decreases of negative values. It can get a little bit confusing. Bottom line, your conclusions aren't going to change. If it makes more sense to you for that mean difference there to be a negative, flip the two conditions until it becomes negative. If it makes more sense to you to conceptualize it as a positive difference, flip those two until it becomes positive. It's, again, not going to change your final conclusion, but it is going to make it easier for you to think about. All right, so there's your mean for the difference. The difference between the two conditions was 0.91. There's your standard deviation as well. And then importantly for our analysis, there is your t-statistic. So it calculates your t-statistic minus 2.12, and that is because our mean difference is negative, our t-statistic is negative. There's your degrees of freedom. And then importantly for us, we are doing a two-sided test. So we look at the two-sided p-value, and it is 0.042. So we are going to now just enter those in. So we have, for our step number 3 here, our t-statistic of the difference was minus 2.120. Got it. All right. Our t-statistic needs a little editing. There we go, minus 2.120. Our degrees of freedom, 31. And then our p-value, 0.042. And now what we're going to do is we're going to finish up our analysis by accepting or rejecting the null hypothesis. And we take a look at our p-value, which is 0.042. We compare it to our alpha, which is 0.05. Our p-value is less than our alpha value, so 0.042, less than 0.045. If your p-value is less than your alpha level, then you reject your null hypothesis and you accept the alternative hypothesis. And we reject that the two conditions are the same or rated at the same discomfort. And we accept that the longer condition was actually rated as less uncomfortable than the short condition. Now, just to finish up our analysis of where you can find useful information on this SPSS output, we have our last table down here, which is the paired samples effect sizes. So if you need to calculate effect sizes, such as Cohen's D, there's your point estimate right there so that you can report those if needed. All right, so any questions on the conclusions or where you can find that information in SPSS? Okay. So let's take a look at how this would then be presented or how this was presented in the wrap-up. So this is from the results of the Kahneman et al. Paper. It goes thus: most subjects indicated that the long trial had caused less overall discomfort. Mean difference equals minus 0.91. T with 31 degrees of freedom equals 2.12. Probability less than 0.05. So there's your mean difference right there. And there's your t-statistic right there. And one thing that you might be noticing is that, well, wait a second. When we did our SPSS, we had a negative t-statistic, right? We had a negative mean difference, and that ended up having a negative t-statistic. That's how t-statistics work. And yet here in the report, he has a negative mean, but he has a positive t-statistic. The reason that this is done, and I don't agree with it, but Kahneman was doing a two-tailed test. And when you do a two-tailed test, oftentimes you report the absolute value of your t-statistic because you have a positive t-statistic and a negative t-statistic, so you just report the positive t-statistic. And it's understood that you are doing a two-tailed, so you don't have to worry about direction. I personally would say, hey, if your mean difference is negative, report the negative t-statistic, even if you're doing a two-tailed. But just don't get confused on that. You might see it both ways. I prefer the one way. Kahneman clearly preferred the other way. Neither is really wrong. Just kind of understand why that might occur. And again, we have this negative mean difference and yet a reported positive t-statistic because this is a two-tailed test. If this was a one-tailed test, then this would be statistically wrong. And the reporting of the positive t-statistic when you have a negative mean difference on a one-tailed test would be incorrect. Anyways, there is the degrees of freedom as well. And then finally, the p-value. And this is a nice indication that the p-value was probably an alpha. Sorry, the alpha value was probably 0.05 because they're reporting less than 0.05, indicating that that was their criteria. Now, I was thinking about doing some of the other t-tests that they ran on other dependent measures. I didn't want to do that because it would take up a little bit more time, but just to kind of show you how tricked the minds of these subjects were, that sentence begins, thus most subjects indicated that the long trial had caused less overall discomfort. So the more painful trial was perceived as having less overall discomfort, And then the next result was less cold at its most extreme moment, even though the two of them were equally cold at their most extreme moment. And finally, was less tough to cope with, even though it was more tough to cope with because it was as tough as the short duration plus an extra 30 seconds of however tough that other water, the 15 degrees Celsius water was. So this is a very, very nice indication that psychologically, our minds, when we are taking into account experiences, and when we're taking into account our memory of experiences, we don't basically average out each moment that we have as an experience. We basically don't average our experiences across this time, because if we did, the long trial would be more painful than the short trial. The accumulated pain in the long trial was objectively more. What it turns out that we seem to be doing, and Kahneman proposes as the peak end rule, is that you don't average every moment of an experience. Rather, you judge it by the peak intensity of the experience and by how it ends. So these two experiences have the same peak intensity. And that peak intensity would have happened somewhere in that 60 seconds at 14 degrees Celsius, 14 degrees Celsius period. But then how it ends, treatment number one ends very intensely. Treatment number two ends intense, but not as intensely. So your mind gets fooled by those final 30 seconds into thinking that it wasn't as bad as the short trial because it ended less painfully than the short trial did, even though you had more pain overall. So this is actually a really nice thing to be aware of, because what it means is that if you are doing something that you find unpleasant, if you're doing something that you find a struggle, I'm not saying tack on another 30 seconds to the end of it and making it even more of a struggle, but you might try to organize your time in a way that the last portion of whatever you are struggling with is an easier thing to do. And then you will perceive the entire effort as being less uncomfortable and less difficult to deal with. So if you're doing a very tough workout, for example, end your workout with a fun cool down that you can enjoy. If you're doing an intense study session, end your study session by studying something that you have a larger interest in or a higher interest in, right? If you're writing an essay, if you have to get an essay done, there are some parts of formatting an essay and writing an essay that I absolutely despise. And then there's other parts of writing an essay that I somewhat despise. And if I needed to work 2 hours on an essay to get it done, I might want to save those less despicable parts of it to the end so that I can trick my mind into thinking that it wasn't so bad. So try that the next time you're doing something that you find uncomfortable, that you find tough, that you find difficult to deal with. Tack on a little bit at the end or schedule a little bit at the end. It's not as hard as the previous portions of it. And maybe when you look back on it, you'll say to yourself, you know what? That actually wasn't too bad. Thank you, Kahneman. All right, so any questions on that paired t-test? All right. Okay, so what we're going to do now is we are going to wrap up our look at the t-test, beginning with the t-test decision tree. So this is going to be a kind of decision tree flow chart that you can follow to always make sure that you're doing the correct t-test for whatever situation. Because in the real world, and when you're reading statistics, oftentimes they will not tell you which t-test you're supposed to do. You just need to read the situation, get the details, and then decide on your own. So when you're reading psychology studies, or when you're doing a psychology study, for example, in your advanced lab, you will have to make the decision of, do I use a 1 sample, a 2 sample, or a paired t-test if that is what your experiment requires. So how would you know? Well, let's start growing this tree. So the first thing you want to ask is, how many groups or how many conditions do you have? That is your first question. And if you only have one group or one condition, then your decision tree is finished. You are doing a 1 sample t-test. So if you have one group of subjects and they experience only one condition, Decision tree finished, you're doing yourself a one sample t-test. On the other hand, if you ask yourself, how many groups or conditions do I have? And you have two groups, or you have two conditions, right? In that case, you need to ask yourself, well, how many conditions did each subject complete? So I have two conditions. How many did each of my subjects complete? If they completed just one per subject, then you have yourself a two sample t-test. You have some of the subjects did one condition, some of the subjects did the other condition. Each subject only completed one condition. That is your two sample t-test. On the other hand, if you ask yourself how many conditions did each subject complete, and the answer is two, subjects did both conditions in your study, then you have yourself a paired t-test. And this decision tree will get you to the right t-test in any situation. Now, you might be thinking to yourself, well, what if I have more than two conditions? What do I do in that case? Well, in that case, you're going to be doing an ANOVA, and we're going to be getting to that in a couple of weeks. It's basically a t-test scaled up to the next level. So the more you understand a t-test, the more you understand ANOVAs. But definitely, this is how you decide which t-test you want to do. Go through the decision tree. How many groups, how many conditions? One sample t-test. Two conditions. How many conditions did each subject complete? Each subject only did one. You got a two sample t-test. Each subject did both conditions. You got yourself a paired t-test. All right. So now our final do it with me demos for the t-test. We're going to take a look at why that decision tree is so important, why it's so important to choose the right test in order to do meaningful, truthful, honest psychology. All right, so let's say that we have a study, and we want to do a study on whether or not having a digital curfew is actually going to improve the quality of sleep for undergraduate students. So does a curfew where you say to yourself, all right, I'm going to bed at 11, and at 10 o'clock, I'm putting away, even though I'm not going to sleep, I'm putting away all digital media. I'm putting away all the screens. I'm turning off my computer. I'm turning off my TV, putting my cell phone away. Will that actually improve the quality of sleep that these individuals are experiencing? So let's say that you are a supervisor of a undergraduate lab in psychology, and actually, no, a graduate lab in psychology, and you have students that are tackling this research. They are designing studies to test this research, to test whether or not this digital curfew is going to help people improve the quality of their sleep. So you send out your grad students and you say, all right, those are your projects. You three go on and do your projects, and then come back and meet with me when you've collected the data, and we'll go over the analysis of the data. All right, so you have your first student comes back maybe a month later, and they say, hey, you know what? I ran the study. Here are the details and the data from my effects of a digital curfew on sleep quality in undergraduate students' projects. So they start giving you the details, and they let you know that in terms of participants, they had 60 undergraduate psychology students, 70% women, mean age 19.6, standard deviation 1.2. Their procedure: all participants completed a 7-day digital curfew, no smartphone use after 11 p.m. A screen time tracking app verified adherence nightly. Participants received standardized reminders at 10:45 p.m. and completed brief morning check-ins to confirm compliance and report notable sleep disruptions. The measures: on day 8, participants completed the revised Pittsburgh Sleep Quality Index global score. 0 to 20 is how the scores can go. Higher values indicate better sleep quality. So this is a sleep quality index. The higher your score, the better you slept over those 7 days. So the analytic plan: the sample's mean revised Pittsburgh Sleep Quality Index score is going to be evaluated against a reference value of 5. And that is a commonly used cutoff to distinguish good versus poor sleepers in validation work. And we're going to use a one-sided t-test because we're predicting that the curfew is going to make sleep better. So the hypothesis is that the mean sleep quality score following a week of digital curfew would be higher than the benchmark of 5, consistent with improved sleep quality under restricted nighttime phone use. So you hear that description and you think to yourself, all right, how many groups or conditions did this grad student have in their design? And in this case, they mentioned that all participants completed a 7-day digital curfew. That was one of the details. All participants completed a 7-day digital curfew. That means that all participants were placed into one condition. If you have only one condition, you have a one sample t-test. So this sample requires, or this design requires, a one sample t-test. And the population mean that we're going to test it against is that reference value of 5 on the revised Pittsburgh Sleep Quality Index scale, because that is the commonly used cutoff for good versus poor sleep. All right, done with the paired. Let's go to the t-test wrap up. Okay, so I really wanted to make sure we didn't get these ones messed up. So we put the students up there. This is going to require one sample t-test. Here we go. So these are the revised, boom, those are the revised Pittsburgh Sleep Quality Index scores. So we have here the 60 students and all of their scores on that scale. And what we're going to do for this one, just in the interest of time, we're going to skip some of the steps in terms of, let's be explicit about the alternative null hypothesis. We're going to go straight into the SPSS analysis. So let's go back to IBM SPSS statistics. We can close out our output from the previous analysis. We want to highlight those two variables and delete them, get rid of them so that we're not confused. And then we go here and we are going to highlight all 60 of those sleep scores. And then we go here and we paste all of them into a single column. We got var 00004, so we go to variable view, and we are going to call that the RPSQI for the revised Pittsburgh Sleep Quality Index scores. So we go back to data view, and if you were using this score repeatedly, that would definitely be enough for you to remember exactly what it is that you were analyzing. So what we do now is we take these scores, we go to analyze, we go to compare means and proportions, we go to one sample t-test, we have our scores over here, we got to move them into the test variables, and then the most important thing here, and again, I'll highlight this one more time because this is where the most mistakes are made when you're learning SPSS, this test value right here, make sure that you change it to the proper test value. So in this case, it's got its default value of 0. That is not what we're looking for. We are looking for our reference value of 5 because according to the Pittsburgh Sleep Quality Index, 5 is your cutoff score for good sleepers versus poor sleepers. So we have our score of 5. We're ready to go. And we hit OK. And we get that output right there. Does everybody have those numbers? Looks good? All right, well, let's see what those numbers tell us. All right, so you do your analysis with the grad student. You get those numbers, you pull it up. I apologize, I called it curfew when I was doing this yesterday. I got to make more notes about what I called the analyses here. But just regardless, let's go straight to the one sample t-test. Check your test value equals 5. But importantly for us, our t statistic here is 9.084. Our degrees of freedom is 59. All of that makes sense so far. We are testing a one-sided hypothesis, a one-sided alternative hypothesis, because we are predicting that sleep scores are going to be better after the curfew. So we take a look at our one-sided p-value, and we see that our p-value is less than 0.001. Incredibly small p-value. Most importantly for our purposes, it is less than an alpha of 0.05. So it's less than an alpha of 0.05, so we would reject the null hypothesis that the digital curfew does not change or does not increase sleep patterns. We would accept the research hypothesis that the digital curfew actually does increase sleep quality. It actually does give you a sleep quality that is higher than that reference value of 5 on that Pittsburgh Sleep Quality Index. All right, is that analysis clear? Okay. So the student, and this you'll experience this too in your academic career when you start doing your own research, seeing that p-value less than 0.05 or less than whatever your alpha is that you set is one of the best experiences you can have in your research. So the student sees that p-value and goes, amazing, a digital curfew increases sleep quality. This is great. And the supervisor is looking at them saying, wow, this is really good. We're going to submit this to a conference. Let me get on the phone. I'm going to talk to the dean. We're going to start putting in sleep programs around campus so they can improve their sleep quality. We can write a book about this, have a YouTube series about the importance of sleep quality. This is excellent, excellent stuff. And then at that point, the next grad student in the lab walks in and they say, wait, hold on. There's been a mistake. You've accidentally grabbed the data from my study, the data that I collected. It wasn't the data you collected. That was actually the data that I collected. And here are the details and data from my effects of a digital curfew on sleep quality in undergraduate students project. So here are the details from project number 2. Whoops, jumped the gun. All right, 60 undergraduate psychology students, 70% women, mean age 19.6, standard deviation 1.2, were randomly assigned to one of 2 conditions: digital curfew, 30 individuals, or no curfew, 30 individuals. Procedure: for 7 nights, the curfew group was instructed to avoid phone use after 11 p.m., while the control group continued typical behavior, screen time apps verified compliance. Measures: on day 8, participants completed the revised Pittsburgh Sleep Quality Index global score. Higher values indicate better sleep quality. Analytic plan: the mean revised Pittsburgh Sleep Quality Index scores were compared between the curfew and the control groups to evaluate differences in sleep quality following the intervention. The hypothesis was that students who observed a digital curfew would report higher sleep quality than those who did not. So it was another study to test the effects of a digital curfew on sleep quality. And in this case, we have a different experimental design. So in this case, we have to ask ourselves, we go through that decision tree. How many conditions were there? And in this case, there was 2 conditions. There was a digital curfew condition, and there was a no curfew condition. So we are no longer doing a 1-sample t-test. We are now into either 2-sample or paired t-test. So we have a digital curfew and a no curfew condition. And then we ask ourselves, how many conditions did each subject participate in? And each subject only participated in 1 condition. You were either one of the 30 people in the digital curfew condition, or you were one of the 30 people in the no curfew condition. Nobody did both conditions. So we have 2 conditions. Subjects are measured only once. That is a 2-sample t-test. So this design requires a 2-sample t-test. Now, just to show you how important it is to choose your tests properly. If you take a look at the scores for this 1-sample t-test, and then you compare them to the scores, there we go, for this 2-sample t-test, notice, take a look at those scores right there. Take a look at those scores right there. They are exactly the same scores. In fact, all 60 of these scores, all 60 of those scores are exactly the same as those 30 scores and then these 30 scores. So to come up with this data here, all I did was take the first 30 scores from this data set and put those into the curfew condition, and then the next 30 scores and put them into the no curfew condition. Importantly, very importantly, exactly the same numbers, but now in a 2-sample t-test designed for an experiment. So let's see what happens in this particular design. So one of the things that I mentioned before is that I'm a little bit better at working with Excel than working with SPSS. So again, we know that we need to get this into a format where there is one score per row because there's only one subject per row. So what I like to do in these situations is I will just take this data, copy it in Excel, paste it right there, put curfew. Let's put that a little bit bigger so we can see what we're doing. Curfew is one of those words that looks like you misspelled it, even though you didn't. And then I just like to kind of work with this in Excel. I find it a little bit easier because I know more of the shortcuts. And now we have it properly formatted for how we're going to put it into SPSS. So that's just kind of to show you, you can do it in Excel and then copy and paste it wholesale into SPSS. So again, we're going to delete this because we're done with that analysis. You can do that, get it all done, get it all in, and that's the method that I like to use. On the other hand, you can do what we did before, which is basically enter in your data, write in curfew, copy that, highlight your curfew group, paste, Control V, and then the same thing with the no curfew condition. Bottom line, as long as we have the scores and they are formatted correctly, it doesn't matter if you do it in Excel or if you do it in SPSS, either one will work. All right, so now we have these two variables here. We have to rename them. So we go over here, and now we can call this the revised Pittsburgh Sleep Quality Index, because those are the revised Pittsburgh Sleep Quality Index scores. And then here we have group. So now we have the actual scores here. We have the actual groups here. Our data is formatted correctly. We go into Analyze, Compare Means and Proportions, Independent Samples t-test, and we're going to put in the RPSQI as the test variable, group as the grouping variable. We're going to define our groups, and we have group number 1 is curfew, 8 characters or less, that's only 6. Group number 2, no curfew, 8 characters on the dot, so we know we're safe. We're not going to come into any issues. We have that set. We don't have to worry about any of the options. We hit OK, and we get ourselves this output here. Does everybody have these numbers? All right. Does anybody need more time to, I mean, I did go a little quick on that one. All right. Okay, so let's take a look at the analysis here. Again, we are going to skip our normal analysis that we would normally do, take the time, go through the group statistics. Although I will point out one really interesting thing. If you take a look at the no curfew condition in the group statistics up here, the no curfew condition has a mean of 7.8. Notice that that is already higher than the cutoff score of 5 for good sleep. So in this case, the one sample t-test had that weakness that we were comparing our sample against the wrong population mean, against the wrong population parameter here, because 5 was too low. It looks like undergraduates, even with no curfew at all, they're already sleeping at like a 7.8 on that sleep scale. So this is possibly going to get us closer to the truth because we're going to be comparing the curfew condition to a correct no curfew condition. So we go to our independent samples t-test. We're going to stick to that top row for this one. So we have our t-statistic of 1.273. We have our degrees of freedom of 58, but importantly for this, we're doing our one-sided we're doing the one-sided p-value because we're predicting better sleep quality after the curfew. And we have a p-value of 0.104. And 0.104 is bigger than 0.05. So this is one of the first examples where we actually ended up with a p-value that is larger than our alpha value. And when a p-value is larger than your alpha value, you reject the alternative hypothesis and you technically fail to reject the null hypothesis, although I will say accept the null hypothesis, even though it's technically wrong in our psychology minds, it makes more sense. So we accept the null hypothesis, we reject the alternative hypothesis because our p-value is greater than alpha. And the result here is too bad. A digital curfew does not change sleep quality. So the exact same data analyzed in a one sample t-test gave us a result that supported the alternative hypothesis. Curfew does increase sleep quality. Now we take a look at it analyzed as a two sample mean, and it actually does not change the sleep quality. So that supervisor that was on the phone all of a sudden says, you know what, I'll have to talk to you later. Sorry, Dean. Hangs up the phone, cancels the YouTube channel, cancels the publication, and basically says, you know what, we got to go back to the drawing board. We got to run another experiment. You know, maybe we can collect some more subjects. Maybe we just need to increase the power of our experiment. Maybe we need a more sensitive measure. You start brainstorming things about maybe, you know, what should be done. We're close, but maybe there's an effect there. We just need to find a better way of measuring it. When all of a sudden, grad student 3 walks in and says, wait, there's been a mistake. You've accidentally grabbed the data from my study. Here are the details and data from my effects of a digital curfew on sleep quality in undergraduate students project. So here are the details from the study that she ran. So participants, 30 undergrad psychology students, 70% women, mean age 19.6, standard deviation 1.2, completed 2 7-day conditions in counterbalanced order. Curfew week with no phone use after 11 p.m. and normal week with no restrictions. Procedures: screen time tracking apps, monitored adherence, a 5-day washout period, separated conditions to minimize any carryover effects. Measures: on day 8 of each condition, participants completed the revised Pittsburgh Sleep Quality Index with a global score where the higher values indicate better sleep quality. Analytic plan: the two conditions were going to be compared, the mean PSQI scores were going to be compared across the two conditions to evaluate the impact of reducing late night phone use on sleep quality. Hypothesis: sleep quality would improve when students limited smartphone use before bedtime relative to their unrestricted week. So again, you have this description of the experiment and you ask yourself, how many conditions do I have? 2 conditions. We have a curfew week and we have a normal week. Those are 2 conditions. How many conditions did each subject participate in? And this time the answer is 2. All subjects went through the curfew week. And then all subjects also went through the normal week. And they were measured after the curfew week and then after the normal week. So in this case, we have 2 conditions. Subjects participated in both conditions. So this requires a paired t-test. So we go back, clear out our SPSS, go back to our t-test wrap-up demo, and now we go to grad student C. There she is. We go to grad student C, and this time we have exactly the same data. So just kind of go back and forth a little bit. Notice that the data is not changing. They're exactly the same number. We have exactly the same 2 conditions, curfew and no curfew condition. The only difference is that these 2 scores come from the same subject in this data set, but these 2 scores come from different subjects in this data set. So again, the exact same numbers, very nicely for a paired t-test. They are already formatted in Excel in the correct manner with 2 scores for each subject on the same row. So we can just highlight all 30 of those scores for curfew and all 30 of the scores for no curfew. We go to IBM's SPSS, hit paste, double check which one is curfew, no curfew. So var 00007, that is curfew. 00008, that is no curfew. Going to keep those below 8 or below in terms of their length of the variables. So we got curfew, we got no curfew, we have the data put in correctly. We go to analyze, we go to compare means and proportions, we go to paired samples t-test. We're going to, long and short are still there. Let's get rid of those. We're going to put in curfew, and we're going to put in no curfew as variable 1 and variable 2. Again, if we want to switch these later, we can always use that little double arrows there. So we have them in there correctly formatted. We hit OK, and now we get this output here. Does everybody have those numbers? All right. So we get that output. Let's take a look at what it means. All right, so we go down here to our paired samples t-test. Remember, do not go to that second table. Paired samples correlations is not your friend. It's a trick, it's a trap. Don't fall for it. But importantly, for here in our paired samples t-test, we have a t-statistic of 6.528. Degrees of freedom is 29, and our one-sided p-value is less than 0.001. So our one-sided p-value is less than 0.001. That is less than our alpha of 0.05. So we reject the null hypothesis and we accept the research hypothesis. And we have evidence now that the curfew actually does increase sleep quality. So the grad student is excited. The professor is about to reach for the phone, but then they say to themselves, well, wait a second. I just got 3 sets of data that were all exactly the same. So some sort of mix-up must have happened. The data maybe wasn't properly labeled. Maybe it was stored in one big shared drive that the lab uses. Whatever it is, this is data that was collected, but we don't know how was it collected. We don't know which experiment design this data came from. And because we don't know which one of those was done correctly. So we don't know if this needs to be a 1-sample t-test for that data, if it needs to be a 2-sample t-test, if it needs to be a paired t-test. Supervisor cannot figure out which one of these is right. And the question is, can you? And the answer is yes, but you're going to have to do some detective work. So if this ever did happen, you would have to track down the actual experiment that the data came from. And whether that means going to the original online surveys or whether that means going to wherever the data was downloaded originally, you're going to have to do some detective work. You're going to have to do some backtracking. This is why it's very important to make sure that your labels on your data are correctly done. But basically, you would have to go back to the design, and then you would have to go through your t-test decision tree and decide which one of those should be done. Because as you saw, the exact same data led to different conclusions. One analysis said, yes, a digital curfew increases sleep quality. The other analysis said, no, digital curfew does nothing for sleep quality. And the last thing that you would want to do is make generalizations and conclusions about a population, about all of the undergraduates in the world. You don't want to offer them advice, give them a theory, give them a conclusion, unless you have the statistical rigor and proper analysis to back that up. And until you do, you would not want to publish this. You would have to go back and find out that data. But importantly, and again, just to drive this home one more time, you absolutely need to know which test you're going to do. Because especially with the paired and the 2-sample t-test, those 2 sets of data are exactly alike. They are labeled exactly alike. They look exactly alike. and SPSS will analyze a two sample or a paired t-test if you ask it to. So if you just take your data and say, hey, I got two samples, so I'm going to do a two sample, and you do not know whether this came from two actual different sets of students or whether they're just the same students measured twice, you cannot do your analysis because you run the risk of a false conclusion because you applied the wrong statistical test. So in that case, again, you're going to have to do some backtracking. You're going to have to go to your t-test decision tree. And then once you discover which one is the correct one, then you go forward with confidence. And whatever the conclusion is, you can state it boldly. You can state it well. You have the evidence to back it up. And you know that you have done your best to help the population of people that you're trying to serve. And you are not going to give them false information, false conclusions based on incorrect statistical analyses. All right. Any final questions on the t-test and the t-statistic? Okay, so that is the t-test all wrapped up with a bow. So what we're going to do next is we are going to be moving on to, I believe, chi-squared analyses, where we take a look at counts and how to analyze those. And then t-tests will come back when we do ANOVAs, because ANOVAs are basically great at telling you that there is a difference in your data, but horrible at telling you where that difference is. So we are going to use ANOVAs and follow-up tests, which are basically t-tests. So practice your t-tests, make sure that you have a good grasp on them. Don't memory dump the whole t-test thing that we have just gone through, because they will come back one more time when we're doing ANOVAs. But as far as t-tests themselves and t-tests proper, that is it for t-tests, and that is it for what I wanted to cover today.